Okay, hi guys. So in this lecture, we'll be discussing on metal oxide film formation. So let's get started. Metal oxide film formation. Okay. So we are assuming that the reaction is first order. Assumption is reaction is first order. And how is metal oxide formed? Metal oxide is formed simply by the reaction of metal with oxygen in the atmosphere. Oxygen to form a layer of metal oxide. And let's say the thickness is represented with a symbol tau. So this is the metal surface. Upon reaction with the oxygen, it forms a thick layer of, rather I should draw it above it, a layer of metal oxide. Like this. This is the thickness of the metal oxide layer, which is represented by tau. Thickness is tau. Okay, so we can write that if tau equals to tau max, then reaction is complete. Okay, and similarly we can write that d tau by dt, that should be equals to the rate of reaction, that should be equals to the formation of metal oxide. So at any point of time the thickness is tau, so we can write d tau by dt would be equals to k tau max minus tau. So this would represent the thickness which has already formed after time t. Okay, and dz by d tau would be k times, k is the reaction constant, times tau max minus tau. Okay, so we can write that d tau by tau max minus tau would be equals to k times dt. Then we integrate it, so we would be getting minus ln tau max minus tau would be equals to kt plus c. So if t equals to 0, then tau would also be equals to 0. So c would be equals to minus tau max, or minus ln tau max. Okay, just substituting the values here, so we would be getting minus ln tau max minus tau would be equals to kt minus ln tau max. So from here we can write that kt would be equals to ln tau max, just rearranging the equation, divided by tau max minus tau. So from here we can write k would be equals to 1 upon t ln tau max divided by tau max minus tau. Okay, so this would be the rate constant in case of metal oxide film formation, and the graph of the same would look like on y-axis if we have ln tau max minus tau, and on x-axis we have t. Then the graph would look like this. Okay, at t equals to 0 it would have the maximum tau max, and at t equals to some time limit this quantity would be going downwards. Okay, so now let's see another concept, which is kinetics of a reversible reaction. So assumption is reaction is elementary in both reactions when we say that Ag plus Bg gives C. So this is the rate constant for forward direction and this is the rate constant for backward direction. Then we are assuming that reaction is elementary in both directions, or in both reactions as well. You can say directions or reactions. Directions. Okay, so if the reaction is elementary in both reactions or directions, we can say that if this reaction is, let's say, second order reaction for the forward direction, this is second order reaction, then this would be a also a second order reaction. Okay, and if this is a first order reaction, then this would also be a first order reaction. Okay, so let's take a different example for a first order reaction in forward and backward direction. Suppose we have Ag plus Bg giving us Cg plus Dg. Then if this is a first order reaction, then this would also be a first order reaction. Okay, so suppose we have an example for this in which first order reaction is opposed by first order reaction. Let's suppose Ag is getting converted into Bg. This is Kf in forward direction and this is Kb in backward direction. So let's say the initial concentration is A here and this is 0. Then concentration at time t would be, let's say, A minus x here and x here, and concentration at equilibrium, let's say, was A minus xe and xe. Okay, so now we want to do the rate of reaction calculations with these concentrations at time t and at equilibrium. So we would be seeing the same in the next lecture. Till then, good luck and goodbye.